In this lesson, we are going to investigate how the principles of electromagnetism are used in a television. Television is an amazing phenomenon that has had a huge impact on society. Some research has shown that television viewing has had a negative effect on the lifestyle and values of many people. However, the effects of television are not all bad. Because of television, people are more informed about world events, and as you are doing right now, can learn by watching TV. Even though many people say they could not be without TV for even a day, most people have no idea how a television actually works. In previous lessons, we have explored links between electricity and magnetism. In this lesson, we are going to apply what we have learned to the movement of charged particles in a magnetic field. It is this behavior of charged particles in a magnetic field that is the basis on which a TV set works. So, by the end of this lesson, you should be able to explain, by applying the right-hand rule, how a television works, and solve simple problems of charged particles moving in a magnetic field. Now, to understand how a modern TV works, let's go back in time to examine a series of inventions that finally led to this amazing invention. The first person we meet on our journey is Heinrich Geissler. He was born in the village of Igelschieb, Germany, and is a well-known figure in the history of scientific instruments, since the descendants of his inventions are still in use today. Heinrich developed his skill as a glass blower working with his father, but then left home and spent a decade as a traveling instrument maker before settling and establishing a workshop in Bonn around 1853. He sold his scientific glass instruments to schools and universities. He participated regularly in world exhibitions, winning several medals for his scientific apparatus. He designed the mercury vacuum pump, which he used to make high vacuum tubes. These high vacuum tubes were the basis of many important scientific discoveries and the first step on the way to the modern TV. Geissler began experimenting with these tubes and filled them with different gases and coated the glass with a combination of chemicals. When he applied a high voltage to the ends of the tubes, they produced a bright luminous effect. The chemicals that produced the glowing light are called phosphors. The tubes became known as Geissler tubes and were sold for demonstrations at universities, schools, and even for home entertainment. The next man we need to meet is Sir William Crookes. Crookes was trained in science by Faraday, Wheatstone, and Stokes, and was active in chemical and physical research for more than 50 years. Like Heinrich Geissler, Crookes made and designed many different vacuum tubes. The most famous of these is called the Crookes tube, which he designed to explore the glowing of phosphors observed in the Geissler tubes. This effect became known as phosphorescence. This tube consists of a glass cone which has the air removed to form a vacuum. There are 3 electrical elements placed inside the tube. At the small end of a glass cone, there is a coil of wire. This end was connected to the negative end of a power supply and was called the cathode. The coil heated up when current passed through it. At the opposite end, the screen was connected to the positive terminal of a power supply. This end was called the anode. The glass anode was painted with phosphors containing zinc sulfide and copper. A flat plate with some distinctive shape was placed between the cathode and the anode. This element was also connected to the cathode. When different voltages are applied to the three elements, the screen will be seen to glow. A non-glowing image of the flat plate will be seen on the screen too. Crookes thought that the cathode was emitting a special ray that caused the phosphor to glow. He called these rays cathode rays. Crookes discovered that a bar magnet placed near the tube caused the cathode rays to move in a spiral instead of moving straight from the cathode to the anode. He also discovered that a horseshoe magnet placed across the path of the cathode rays caused these rays to bend in a curve. However, Crookes was not totally correct about the nature of his cathode rays. In 1897, J.J. Thomson proved that cathode rays were streams of particles that carried a negative charge. He showed that these particles were 2,000 times lighter than the hydrogen atom. He called them electrons. So when a Crookes tube is turned on, the cathode rays are actually a stream of electrons. These moving negatively charged particles will normally be accelerated from the negatively charged cathode towards the positively charged anode. When the stream of electrons touches the phosphors painted onto the inside of the glass tube, the phosphors glow. Both Crookes and Thomson showed that the moving electrons change direction when entering a magnetic field that is applied at 90 degrees to the motion of the electrons. Remember that an object only changes direction when acted on by a force. Can you think why there is a force exerted on a moving stream of electrons when they enter a magnetic field? Well, think back to what we have learned about Ooster's discovery. He showed that whenever a current moved through a conductor, a magnetic field would be set up around the conductor at right angles to the direction of the current. But remember also that a current is in fact the movement of charged particles inside the conductor. We define the direction of conventional current as the movement of positively charged particles from the positive to the negative terminal of a battery of a circuit. So in a Crookes tube, we have a stream of electrons moving from the negative to the positive terminal. This is in the opposite direction to conventional current. But the moving electrons still set up a magnetic field at 90 degrees to the direction of motion. So when the moving electrons enter the area of the tube where there is a strong magnetic field, the electrons will experience a force due to the interaction between the two magnetic fields. As a result, the stream of electrons will experience a force causing a change in directions. Again, we can determine the direction that the charged particles will move in by using the right-hand rule. Here I have a stream of electrons moving from left to right. This stream moves into a magnetic field with a north pole behind the stream and a south pole in front of the stream. Now, when a stream of negatively charged particles moves from left to right, we point the fingers of the right hand in the opposite direction. That is the direction of conventional current, from right to left. Next, we turn the fingers of the right hand in the direction of the magnetic field, from north to south. Now my thumb points upwards, indicating the direction of force on the stream of electrons. The magnitude of this force depends on three things: the magnitude of the charge on each particle, Q, the velocity of the particle, V, and the size of the magnetic field, B. We can express this in an equation as F equals Q times V times B when the direction of the charged particles and the direction of the magnetic field are at 90 degrees to each other. Now, how can we apply this to making a television? Well, in 1897, Karl Braun, a German physicist, added to the works Crookes had done and developed a special cathode ray tube with an arrangement of electromagnets that were used to deflect the stream of electrons. His tube was in fact the first oscilloscope and was modified slightly to make the first electrical television during the 1920s. You should never open up a television set since they are high voltage devices. They also contain capacitors which can store large amounts of charge, which can give you a very serious shock. We have asked an engineer to open this set for us, and he is now going to help us take it apart. This will give us the chance to see how things have changed since the days of Crookes and Braun. Let's take a look at the inside of this TV and review the different components. Here is the cathode, and this is the anode. The electron beam does not just travel straight towards the anode. There are two sets of electromagnets that control the movement of the beam. By controlling the voltages applied to the electromagnets, the direction of the electron beam can be changed. This is the stream of electrons being accelerated towards the screen coated with phosphors. One set of electromagnets can shift the beam vertically up or down, while the other set of electromagnets adjusts the beam from left to right. Now, when the high-energy electron beam strikes the anode, the phosphor-coated screen glows. In a black and white screen, there is one phosphor. This glows white when struck. The electron beam paints an image onto the screen by moving across the screen, one line at a time. To paint the entire screen, electronic circuits inside the TV use the magnetic coils to move the electron beam in a special way called a raster scan pattern across and down the screen. The beam paints one line across the screen, from left to right. It then quickly flies back to the left side, moves down slightly, and paints another horizontal line until the whole screen is painted. Then it moves to the top of the screen and starts again. In this way, the screen is painted 50 times per second. As the beam paints each line from left to right, the intensity of the beam is changed to create different shades of black, gray, and white across the screen. Because the lines are spaced very closely together, your brain groups all the glowing dots together to form a single image. A color TV screen differs from a black and white screen in three ways. Firstly, in a color TV, there are three electron beams that move together across the screen. They are named the red, green, and blue beams. The second way that a color TV is different is that the screen of a color TV is not coated with a single sheet of white phosphor, as in black and white TVs. Instead, the screen is coated with red, green, and blue phosphors arranged in dots or stripes. If you turn on your TV and look closely at the screen with a magnifying glass, you'll be able to see the dots or stripes. Thirdly, on the inside of the tube, very close to the phosphor coating, there is a thin metal screen called a shadow mask. This mask is perforated with very small holes that are aligned with the phosphor dots or stripes on the screen. When a color TV needs to create a red dot, it fires the red beam at the red phosphor, similarly for green and blue dots. To create a white dot, red, green, and blue beams are fired together. The three colors mix together to create white. To create a black dot, all three beams are turned off as they scan past the dot. All other colors on a TV screen are combinations of red, green, and blue. The brain combines all these dots to form a moving image. Amazing, eh? Now, to wrap up this series on electromagnetism, I want you to notice that all the principles of electromagnetism are applied in making a television work. The high potential difference that is required to get the electron beam to accelerate from the cathode to the anode can only be produced by a step-up transformer. Notice too that the electromagnets are used to steer the beam across the screen, and of course the moving beam is deflected by the magnetic field to form the image. I wonder what Oostad and Faraday would say if they could see how their discoveries have been developed. Now here's your task for today. This diagram shows the electron beam passing between the two horizontal controlling electromagnets. If the beam starts on the left of the screen and moves to the right, use the right-hand rule to show how the magnetic field changes during the motion of the beam. In your answer, you will need to draw a series of diagrams to illustrate what happens. Here is your second task. The electron beam moves from the cathode to the anode at a speed of 3 × 10 to the 8 meters per second. The charge on the electron is 1,9 × 10 to the minus 19 coulombs, and the magnetic field has a strength of 0,2 Tesla. Calculate the force exerted on one electron. From early beginnings, the study of electromagnetism has taken us on a long journey. However, the journey continues. Scientists accelerate particles through large electric and magnetic fields in order to unlock the mysteries of the atom, and electrical engineers look for new ways to generate, distribute, and use electricity. And so the revolution started by Oostad and Faraday continues. Goodbye.